Hello everyone, welcome to the practice section for Unit 8. My name is Jiang Jiang from Nanjing Forestry University. In this unit, you have learned the roadmap for ecological forecasting and the architecture of EcoPad. In this section, we will practice the ecological forecasting at the spruce site using carbon chain. We will go over some procedures for ecological forecasting when do the practice. You must have seen this diagram several times during our workshop. To get a realistic projection of terrestrial ecosystem carbon dynamics, there should be three steps. First, we need a good model structure, which represents underlying ecosystem processes. Then we need a good parameterization method to estimate parameter values. For example, data assimilation techniques used in this workshop. Finally, we also need a workflow system to link real-time forcing to the model. Carbon cycle models usually need forcing data to drive the projections. For this purpose, we developed a ecological platform for assimilating data into model, which named EcoPath. In the traditional way, people usually tune the model, fit the data, and then get output of forecasting. This is forward method. EcoPad is an inverse and interactive method which links data and model in data assimilation system to optimize the parameters. It can be real-time forecasting. The system can update parameter distribution when new data is available. From ensemble of parameters, EcoPad can also produce ensemble of forecasting instead of just one simulation, which allows to us to quantify the uncertainty of forecasting. This diagram shows how EcoPad works technically. We need two kinds of dataset, observation data and forcing data. Observation data is used to optimize the model parameters through data assimilation techniques. We also need forcing data to drive the model, which is usually climate data in carbon cycle models. So next, I'll talk about the application of EcoPad at spruce site using carbon chain. Remind you that spruce experiments has two treatments. One is warming with different level of both above ground and below ground temperature increment. The other is elevate CO2. First, let's look at the observation data at spruce site. Before the treatments were initiated, the spruce site had measurements of basic carbon cycle from ambient plot, including CO2 flux, foliage biomass, wood biomass, root biomass. They also collect the initial peat carbon and the phenology data. Then look at the forcing data. From the spruce site, we have climate data from 2011 to 2014, which include air temperature, soil temperature, relative humidity, and wind speed, precipitation, and PAR. But this is not enough. To make a projection of carbon cycle, we also need the future forcing data. In this study, we use a stochastic weather generator to produce hourly precipitation and temperature from a R package. And we also generate the other climate data randomly draw from frequency distribution at a given hour of each month. For the practice purpose, we already generated 300 trajectory of forcing data from 2015 to 2020. 24 and store them in carbon chain. To make model projection, we can randomly choose the forcing trajectory to represent uncertainty of forcing. But in real operation, you may use updated weather forecast data as forcing to drive TICO model. So now let's get started to the practice. Please follow the instructions to launch carbon chain. Practice 1. How constrained posterior parameters influence forecasting uncertainty. In this practice, you will run data simulation with different sets of parameters to get outputs of constrained parameters. You have already learned this part from yesterday's Unit 7 practice. And then run the forecasting with different DA output. Here are the steps to generate different sets of constraint parameters. So here, once you click the button of select DA path, you will allow you to set the parameters to either 1 or 0. So here the 1 means the parameters are selected for data simulation and 0 is not being selected. You can see here 18 of the parameters are selected. This is also the maximum of the parameters allowed to be selected. You may change the 1 to 0 if you don't want the parameter to participate in data simulation. Please continue follow the steps. So in my personal computer, it took 10 hours when the number of iteration is 20,000. So you may change the number to smaller values, but small number of iteration will result in unconstrained parameters. So in a formal data simulation procedure, it usually takes millions of iterations to get to a stable constraint parameters. Now let's do the forecasting. This is an example of data simulation results from Unit 7 with 18 default parameters. You can see that some parameters were constrained well, for example, the SLA, specific leaf area, and VC max for the photosynthesis, turnover rate or roots. But some parameters such as GL max, GR max, the maximum growth rate, are not constrained well. Here are the forecasting output for the leaf, wood, and root pool-based carbon, and also flux-based carbon such as GPP, NEE, and ecosystem respiration. You can see here the model simulation can basically capture the observation data, except that it overestimates the respiration. And for the leaf carbon, the model simulation underestimates the rapid accumulation of leaf biomass. And this is another set of forecasting. Now the model simulation can capture the leaf carbon. However, it failed to simulate wood and root carbon. So you can try to run other forecasting using different data simulation output, but this is time consuming. So I will move to the next practice, how different forcing influence forecasting uncertainty. In this practice, you will compare the forecasting difference between one single trajectory of climate forcing and 100 random trajectory of climate forcing data. So compare the forecasting uncertainties. You can see that when using one single trajectory of forcing data, that's bottom right, the model generate diverse results, and especially for the pool-based carbon. Okay, practice 3 is to explore the effect of temperature and CO2 treatment on forecasting uncertainty. Here are the example of forecasting from temperature and CO2 treatment. Both warming and elevated CO2 increased carbon stock in forage, wood, root, and soil. But uncertainty in forecasting reduced the statistical power to detect the treatment effect. The plant compartments have stronger response to either warming or elevate CO2 than soil carbon. The difference between response between the ambient and elevated CO2 were more likely significant at higher temperature treatment. So if you are interested, you can further explore the relative contribution of forcing and parameter uncertainty to the forecasting uncertainty. So for example, the uncertainty of carbon cycle model result, it can stem from three fundamental components. So rely on the model structure, parameterization, and external forcing. So here we use a Spruce data to investigate the relative contribution of forcing and parameter uncertainty in the forecasting of terrestrial carbon cycle. So you can uh, follow my paper and to look at some of the results. Here we found that the external forcing cause higher uncertainty than parameters in forecasting carbon cycle, while the external forcing cause lower uncertainty than parameters in forecasting the pool size parameters. Okay, thank you.